Continue from previous video solving these two slabs. Now we like to assume these N12 bars for the main reinforcement. Generally in the slab we use N12 bar and N16 bars. Now a subscript supports that I already discussed in the last video, that is just basically the center, from the center of these supports to the edge. So 500 is the width of the beam. I think I can show it to you in the examples that we have. If you are looking for these cross sections here, 700 millimeter depth, 500 millimeter is the width. So the width of this beam is the 500. I just draw these cross sections here. So it's 250 millimeters. Now I already also explained you these definitions, where shorter length you denote it as a 5.5 meters. So I just redraw this corner slab here, this corner slab that we are working on. I just redraw it here. So 5.5 meters, that's 5.5 meters coming from here, and 7.5 meters is coming from here. In this one we can identify this 5.5 is a short length, so it's LX, and this LY is the longer length, so it's let's say 7.5 meters. Now LOX, in the last video, if you note in my previous video where we have these figures, where we talk about this LO value, this LO is found by using this one. Please refer to the last video. So LOX is 5500, which is the L, that is L, that is given in our examples. Take away 2, both side 250, so 2 times 250 times by 0.7, and then you can find LOX is equal to 5150. Similarly LOY, you can find LOY 7500 times 2 times 250 both side times 0.7. That will give us this 7150 millimeter. So we generally need this ratio LY on LX, which is LOX on LOY, that I substitute this value, is give me 1.39 no unit. That is just the length ratio. Now we are going to use these equations, that is called Deem to conform span to depth ratio for the reinforced slabs. Now in this one they have given you two clause. The clause number 9.4.1 is a one-way slab and two-way flat slab. And over the page, if you make it the one page over, here they have given you this clause 9.4.4.2, which is talking about rectangular slab supported on the four sides. So that's our intentions, that we can use this 9.4.4 rectangular slab supported on the four sides. Now if you can read this one, they are basically the same equations that is over the page, these equations, but just the difference is K3 and K4 that we going to extract it from here. So we are going to work on these equations, but only difference for rectangular two-way slab where four edges are supported, you will have these equations. Now I copy these equations. Let me identify the each parameters. That LEF on the left side here, that is called effective spans, and in the last video we talk about what is the effective span. This small d is the effective depth. Now the effective depth, I can draw the small pictures here. That effective depth is basically, if you are talking about the slab of the depth, then we assume these N12 bars. Here we assume N12 bars. So this total depth is denoted as ds. Okay, so that is the depth of the slab. Now the effective depth is measured from the center of the bar to the top of that edge, so that will be effective depth, and that is basically depth. ds, take away half of this reinforcement, take away this cover, will give me this small d, which is the effective depth. We will calculate that one that time over. Thanks. Delta over LEF is a deflection limits. K3 is 1. If you go back in the clause 9.4.42 over here over the page, it has written K3 equal to 1 straight away for rectangular slab supported on the four sides. K4 deflection constants, we will work on that one. Now FD effective, which is the effective design load per unit area, that written here, effective design service load per unit area, and that is in the kilopascals. There are two equations given to calculate this effective design load per unit area. Let's calculate that effective design load per unit area. That equations has given 2. Now we are working with the total deflections. We need to calculate the total deflection. So I am taking this equation A, that I copied here. I'm not reading these parameters. I will discuss those parameters, each parameters one by one. Now let's start talking with KCS. Now KCS, as we talk about in our deflection calculation, that is called creep and shrinkage factors, KCS, and that KCS equations given in clause 8.5.3.2. Now let me go back to that clause for you. So that clause is here, 8.5.3.2, where you have this long-term deflections, and you can read about this note, but basically we are using these equations that I copied here. Now for the slabs, if you are in the if you are, let's say, talking about this Deem slab, in this zone, in the mid span, you have sagging. The beam are sags. Okay, so we provide the tension side is at the bottom, so we provide the bottom tensile reinforcement. At the supports, the beam will hogging, right? So we provide the tensile reinforcement at the top of the edge. And please note, in the slabs, we don't provide the compression reinforcements, unlike the beam. So we generally have this tensile reinforcement. That's written here. Now in that case, ASC, compression reinforcement, area of compression reinforcement is 0. If I substitute the value 0 here, that is make this 0, that will give me the 2. And standard wants me to check whether the value calculated KCS is greater than 0.8. So it's yes, 0.8. That is okay. So I calculate KCS equal to 2. And now let me go back to that page where we are talking about the Deem to conform span to depth ratio. So that is here. Now continue working on this. This G is the dead load, and in the last video, in the previous video, we calculated that G. I can show it to you here. I just need to find it. That G value we calculated, here you go. That QG we calculated, that is 4.7 kilopascals. That is the your dead load. And live load also given in the questions that we noted here, which is live load is 3 kilopascals, that are written here. Now short term load factors is 0.7, that is given in the questions. If you go back to the questions, it has given you this short term load factors 0.7, and long term load factor is given 0.4. In case it's not given in the questions, you can refer to the AS 1170.0 on page number 16. They have give you these tables. For office and residential, domestic building and parking, it has given you 0.7 and it will be 0.4. It's very easy to, you can read here and you can very easily to find these short-term load factors and long-term load factors given here, but it's given in the question, so there is no problem. But if it's not given, you can extract this from the AS 1170.0. Now let's continue working on that. I think we have all the required details. Again, I copied this equation from the standards. 1 plus KCS, we just found KCS is 2, that I substitute here. G, we noted dead load, which is 4.7 kilopascals, plus short-term load factors 0.7, substitute here, plus KCS, that is creep and shrinkage factors 2, times long-term factor 0.4, and live load is 3 kilopascals. Substitute here, it gives me 18.6 kilopascals. The unit kilopascals is given here, that we need to take this unit as a kilopascals. Thank you. We can continue solving these examples in the next video using these equations. Thank you very much.